So welcome back, everybody. And it's time for a completely different topic than last time. But if there are any questions about what I talked about for the last two lectures, I'm happy to answer them before I go on to something much sparser, which are graphs. We're also going to have an announcement probably later today. Razvan wants to say a few words about the homework. So if there are any questions about that, that's a fine thing to talk about too. So this lecture will fill 1.5. So here's an outline of the next 1.5 lectures. And because there's a lot of interesting ideas, and this is such an important problem, I'll also give you pointers to a bunch of software, because people have built a lot of tools to solve this problem already. And the reason there's so much software is there's no one right way to do it, which is why I'm spending a while to tell you about it and why there's so many different pieces of software to point you to. So I'm going to review what the graph partitioning problem is. And we've seen it before when we talk about sparse matrix vector multiply. The idea is a graph is a bunch of vertices connected by edges. The vertices are going to represent work that you want to assign to different processors. And the edges are going to represent communication, how much one task, one vertex has to talk to another. So you want to give all of the vertices, spread them out, partition it so each processor gets about an equal amount of work to do, and so that there are as few edges crossing between processors as possible. So they have to communicate as little as possible. And so I'll remind you of that notation in the next slide. Then I'll give you an overview of the heuristics. This turns out to get the absolute perfect answer, it's NP hard, so it's exponentially expensive. So that's why there's so many heuristics, and there is no one right way to do it. And I'm going to divide the heuristics into two categories, depending on what extra information you may or may not have with your graph. The first category is you have nodal coordinates. That means each vertex not is just a vertex, but it has an xy coordinate or an xyz coordinate. That comes up pretty frequently, for example, in finite element modeling or something where you're partitioning space. And in that case, you can use that extra information to go faster. And the assumption is you're only connected to your nearest neighbors, which is pretty typical in finite element modeling. But a lot of graphs that people care about don't have coordinates, or you're certainly not connected to your nearest neighbors in any reasonable physical sense. So for example, in the World Wide Web, the nodes are web pages and the edges are links. This web page refers to that one, and you want to partition that somehow and ask questions about it. There's no geography that makes sense there. So I'm going to give you the basic techniques that work for both those categories of graphs. And then I will tell you how to make them run much faster, both of them, using a big idea. Now, why am I calling this a big idea? It's because it's going to appear not just in this lecture, but in lots of others too, and that is multi-level acceleration. If your graph is too big to run the basic algorithms I'm going to talk about up here, what are you going to do about it? The answer is you're going to take your graph and approximate it with one about half as big by somehow throwing away half the vertices and half the edges. And then you'll run the algorithm, the problem that's half as big, and use that as a starting guess for your original graph. Now if you have an enormous graph and only throw away half of it, it's still pretty big. How are you going to solve the half-size problem? Well, just do it recursively. Throw away half of it, and you'll get a whole kind of recursive algorithm to do it. And that's the big idea that appears over and over again in lots of different problems. Then I'll have some data, some comparisons of the performance of these. And this is, the multi-level stuff will be next time. I won't get that far today. Then I'll compare a bunch of different methods and applications using some data. And then it turns out there's a model that people like to use recently, which is to model communication in tasks. They're not graphs, they're called hypergraphs. And they're a more accurate description of who has to talk to whom. But we'll save that for next time. So let me go on to graphs. And so here's all the notation I'm going to use. A graph consists of a set of nodes or vertices. I'll probably go back and forth between the notation, a set of edges connecting them. And then node weights, think of those as the amount of work that is involved in each node. And the edge weights, which is how much actually has to be communicated across it, because not every task or communication is created equal. So here's a picture, and I've labeled everything quite thoroughly. In parentheses are all the weights of both the vertices and the edges. And so what I'd like to do is, as I said, the nodes represent the tasks, the weights represent the costs, the edges means that one task has to talk to another, and the edge weight is how much it has to communicate. So if I have p processors, my goal is to partition the vertices, the task, into p pieces so that the sum of the vertex weights are about the same in each partition, so each processor has about an equal amount of work to do. And the sum of all the edge weights connecting different vertices in different partitions is as small as possible. And so just to do that particular example for this picture up here, let's suppose I had 4 processors. I might choose to partition it that way. And in that case, have I done a good job in the Task balancing, well, how much does the purple processor have to do? 3 plus 1, so he has 4 units of work. 1 plus 3, 4 units of work. 2 plus 2, 4 units of work. 1 plus 2, okay, so close. And how much communication has to happen? Well, I only count the stuff on the edges that go from one processor to another, from one color to another. So in this case, these two edges, 2 and 3, so the blue processor has to communicate 5 units of stuff to the green. And green and orange and red have to communicate just 1 plus 2 or 3, so that's what happens. So when you have P processors, of course, that's what you want to do. It turns out that most of the algorithms that we have are going to be based on just dividing into two parts. They're called graph bisection. And of course, what happens if I have more processors? I'll just apply this idea recursively, divide it into 2, then 4, then 8. So almost all the algorithms are going to be for the graph bisection problem. So this has a long intellectual history. It was invented originally to design the telephone network, AT&T. And there was a person there working for Bell Labs called Kernighan. And he invented the first algorithm, and we still use that basic algorithm, well, the idea, a much faster implementation of it. So who else knows what Kernighan invented? Yes, he wrote the first C textbook. There are a few other things. He wrote the first Hello World program. If you've ever used awk in Unix, he's the K. And he also made up the name Unix. So he invented a lot of things early on, including this algorithm. So that was the original one, and it was very small graphs at the time. Load balancing while minimizing communication, that's sort of the common theme that we have here. And one example that I used before, and I'll use again, is sparse matrix vector multiplication. And in fact, a graph and a sparse matrix are kind of just different mathematical terms for the same thing, so it's a perfectly natural thing to do with it. And so in that case, I will have one node for each row and column in the matrix. And I'll have a non-zero in the matrix. That corresponds exactly to where the edges are. And what I want to do then, my partitioning problem, is I want to assign rows of the matrix to different processors. They'll be responsible for doing the dot products of those rows with the vector x. And so what is the node cost going to be? Well, how much work does it take to take a dot product of one row with a vector? It's the number of non-zeros in that row. And the edge weights are just 1. I'm sending one word there. So another example where people use this is VLSI layout. You have a bunch of processors that you want to lay down on a chip. They're connected by wires, and you want to put the stuff that has to communicate a lot close together on the chip, so you don't have to spend too much time or much energy pushing a lot of information along the thick wires between different components. So another example is reordering the rows and columns in a big sparse matrix before you do Gaussian elimination. I think I've showed you a picture of that before. Depending on the order of the rows and columns, you may get more non-zeros filling in as you're doing the elimination. You want to minimize the number of fill-ins. And it turns out the same graph partitioning problem helps us solve that. Will let us sort of minimize the amount of fill-in. So, and here are a lot of other examples. Let me just mention the last one, image segmentation. That was pioneered by Jitendra Malik, who's here in the ECS department. And in that case, and I showed you a picture, I think, of a koala climbing a tree when I talked about tricks with trees lecture and how do you do parallel prefix. Well, what you actually do after you compute all of those information about how much each pixel is related to each other pixel is you do a graph partitioning problem on that graph on the pixels to decide where's the koala, where's the tree, where's all the other stuff. So it comes up there as well, and he was the one who pioneered that. So let me just do one more slide of notation to connect sparse matrices to graphs. And so here I have 2 pictures of the same thing, an 8 by 8 matrix and a graph with 8 vertices. And there's one row or column per vertex. And for every non-zero, except for the guys in the diagonal, that's a vertex connected to itself. I don't bother drawing those. I have an edge, so if there's an edge, there's a non-zero in the 1, 2 entry, so I have an edge from 1 to 2. There's a non-zero in the 1, 3 entry, so I hope, yes, there's an edge from 1 to 3. And so what I'd like to do is assign rows of this to processors, and I'm going to describe in English what the sparse matrix vector multiply algorithm is, and here it is all written out in code if you want to read it. So the blue processor will own the first 2 rows, the red processor will own the rows 3 and 4 and so forth, so that's what the partitioning is, and here the coloring goes too. And so if processor 1's job is to do the dot product of these first 2 rows of the matrix with my vector x, what information has to move along? Well, I need to know x3, x4, and x5. And so if I look at the edges here, I see that I'm connected to 5, 5, and 3 and 4, right? So I need all those. So the first row needs x3, and it needs x5, and the second row needs x4 and x5. And there's x4 and there's x5. So each of those edges represents a value of the x vector that has to be communicated from whoever owns it, say the red processor to the blue processor. And so you can imagine now that you're writing your n-body code, you have to put in a lot of sends and receives, and all of that stuff is written down there at the bottom of the slide. But it's the partitioning that tells you how many sends and receives you're going to have to do. So let's talk about the cost of that algorithm. If we did it in the obvious way and we insisted on getting the best possible answer, any possible partitioning is fair game, could be the right answer. And so let's just count for fun. If I only wanted to divide the graph into two parts, how many combinations are there? So that's n choose n over 2, different ways I can choose a subset of n over 2 vertices out of n. And if you do the little bit of combinatorics, that's about 2 to the n possibilities. And so we're not going to do that. And so that's why we have so many heuristics, and that's why in this talk there is no one best heuristic. It depends on the properties of your graph, and that's why so many software tools have been invented that you should not reinvent. You should use them if possible. And so, but you need to know something about your graph and have some intuition so you know which is the right tool to use. And so let's go on now to give an overview of the heuristics. So the first heuristic, as I said, is we're going to do repeated bisection. If I have 1,024 processors, I'm not going to, in one step, divide into 1,024. I'm going to divide it into half and do that 10 times recursively. And so, henceforth, I'm mostly going to discuss graph bisection. And so here's a picture just to keep in mind. Here's a graph that you encounter every day, obviously. And I wanted to find some set of edges that if I remove them down the middle, those are the red ones, I'm left with this connected component and that connected component, and I hopefully haven't cut too many edges. Now in this particular picture, I've removed edges. That's how I've separated the graph. But there's actually algorithms that work two different ways. They either remove edges, the way I just showed you, to break it into two parts, or they remove vertices. And they just, because different heuristics work differently. And it turns out either one is good enough. We can use either one to get another one. And so I just want to, and I'm going to use both of those, whatever is convenient as I go along, so I just want to define it here. So an edge separator is E sub s, that's a subset of the edges, and if I take it out, then what I've done is I've disconnected the graph into two separate parts, the nodes of subset n1 and the node subset n2. So here, in this simple two-dimensional grid, everybody's connected to their four neighbors. The green set is a set of edge separators. Obviously, if I take out the green vertices, the green edges, I've broken it into the left half and the right half. And ditto for the blue ones. That's a different edge separator. They're equally good. The other thing is a vertex separator. That's a subset of the vertices. And they have the property that if I take them out and all the edges that they touch, then I've also broken up the rest of the graph into two separate parts, n1 and n2. So here, what's the natural vertex separator? It's all the red vertices, because if I remove them and all of their incident edges, so that's the green ones and the blue ones and all these vertical ones, I've also broken that up into two halves. And as I said, some heuristics give you an E sub s and some heuristics give you an n sub s. And so, but it's okay, I can go back and forth between them, it's pretty easy. So suppose I give you an edge separator, but you really want a vertex separator for some reason. What do? You just pick one endpoint of each edge. So if I give you all of these green guys, those are an edge separator, and I want a vertex one, I'll just pick either the left or the right endpoint of each one. That's good enough. And I can go the other way too. I can make an edge separator from a vertex separator, just take all the edges that touch those vertices. And now that can grow a little bit more. If D is the degree of the graph, that means if I have at most here 4 neighbors, so D equals 4, I might cut as many as 4 times as many vertices. And in a lot of cases that's good enough. So as I said, we'll do either one, whichever is convenient. Okay, so here are the other two categories of the heuristics. So it depends on whether I have xy or xyz coordinates for all of my graph, for all the vertices or not. And here's an example. It's built into MATLAB. You can just sort of call it up and look at it anytime you feel like it. So it's a finite element mesh which is doing adaptive mesh refinement, so it gets much finer around near the surface of the wing so that you can resolve the turbulence there. And I want to break that up and spread it out over a bunch of processors. And I'm going to use the xy coordinates of all those points. But if I have the World Wide Web, then obviously I don't have XY coordinates that mean anything particularly. And so a typical graph there would be, one row for each web page and, one row for each keyword and one column for each web page. That's a common thing that Google uses to do search. And then we'll do the multi-level acceleration next time. Okay, so that's the overview. And the next step is to go back and do the nodal coordinate case, where we assume we have XY or XYZ coordinates. And so let me give you a classic theorem that gives you a hint of how well we hope to be able to do with the heuristics. And it's going to be the special case of what's called a planar graph. So a planar graph is what all professors draw on the board. You put a bunch of vertices there and you draw the edges. But the assumption is I can draw it without edge crossings, right? That's what a planar graph is. So so you can imagine if I had if I had a lot of vertices and everybody was connected to everybody, I couldn't draw it on the board without those lines crossing one another. So a planar graph says I can draw it without any two edges crossing. So a typical example is a two-dimensional mesh, but it's much more general. So so the question is, let me go back to this picture of this particular planar graph. And here it's pretty easy to see if this were an n by n collection of vertices, so n squared altogether, how big is the separator? Well, it's the square root of the total number of vertices in this obvious square case. That turns out to be true for any planar graph. And that's going to be our goal in general to reach that. So here is the theorem that says if G is any planar graph, then you can find a vertex separator with the property that it partitions it. So if you take those out, vertices out, you're left with the guys on, let's say, the left and the guys on the right. And you've only had to take out a square root of the number of vertices, a factor of 8. And it's pretty good at load balancing. It's not 50-50, but this says that neither of the two halves that you broke it into can be more than twice as large as the other. They're between 1/3 and 2/3 of the total. And that's true for any graph. And that's a famous deep theorem. I'm not going to prove it, but it's going to be our goal. It gives us our target for what we want to do in 2 dimensions, and we'll also think about what it means in 3 dimensions. So let me talk about the first heuristic that we're going to use. It's called inertial partitioning, and I'll give the physics intuition for where that name comes from on the next slide. And I'm going to draw it in 2 dimensions, but it works in more. And so what I'm going to do for a graph in 2 dimensions is choose a line with half the nodes on one side and half the nodes on the other. And the question is, how do I pick that straight line in 2 dimensions or a plane in 3 dimensions? And so the algorithm I'm going to show you step by step, but I'm going to choose a magic line, capital L. And then, and that I'll explain how to choose capital L on the next slide. But on this slide, I'll say, once I've chosen that capital L, how do I choose the actual dividing line, which is going to be perpendicular to it? Okay, so what I'm going to do is I'm going to choose this line in a way I'm going to describe in the next slide. And what I'm going to do is draw a line perpendicular to it, L perp, and I'll take all the points on one side of L perp and all the points on the other side of L perp. So how am I going to do that? So suppose I'm given this line. How do you define a line? Well, I'm going to give you a point that it goes through, x bar, y bar, and I'll give you a perpendicular to it, right? So that's enough to determine a line. So here's the picture. I'll give you a point, the line goes through, and then the perpendicular. And that'll be the equation of the line. The next step is take each point and project it to the line. So just draw the perpendicular from each of my points to there. And that's easy to do. You do a little dot product. So these S's are the coordinates of all those points. And then what I want to do is divide those in half. So what I'm going to do is compute the median, right? So half of the projections are on that side of the red dot, half are on that side. And that's how I'm going to be dividing it. What I'm going to do is basically use the median to partition the nodes. Everybody on that side will go into one half, everybody on that side will go in the other. That's certainly going to guarantee I get a good load balance. And where is this perpendicular line? It's the line that goes through that median point, and it's perpendicular to the line I started with. So that's the L perp that's going to divide the vertices into this half and that half. And so all of that is very straightforward algebra. The question is, what's the best choice of capital L? It all depends on a good choice of capital L. So let me show you two choices for an example of capital L, a good one and a bad one, and then generalize. So here is a 2-dimensional mesh, but a long, skinny 2-dimensional mesh. And here are 2 possible choices of the line capital L, down the middle and perpendicular to it. Now if I choose L down the middle, the L perp that comes out is right there, and I get 4 edge crossings, and that's intuitively a very good idea. And if I choose L in this rather bad way, the best L perp I can do is that, and I get 13 edge crossings. That's a really bad idea. So how do I naturally describe L, this L, as being better than that L? What I'm going to do is choose capital L to be a total least squares fit of all these points. I'm going to choose capital L so that the sum of the squares of the distances from each point to that line is minimized, right? That's a least squares problem. And so, in other words, if I go back to this picture, I would want the sum of the squares of the lengths of all those green lines to be as small as possible over all possible choices of capital L. Now, why is this called inertial partitioning? Because here's the physics problem. Imagine this is some rigid body where there's, where each of these has a mass, a particular, each one of those weighs a pound or something. And what I want to do is spin this around, and I want to make it as easy to spin as possible. How do you measure how hard it is to spin this around a particular axis, capital L? It's called the moment of inertia. And so what I want to do is minimize the inertia over all possible choices of L, and that's exactly the same problem, which is where the name inertial partitioning comes from. Okay, so the next question is, how do I compute this least squares fit capital L? So that turns out to be one more simple page of algebra, which I'll show you. So here's the picture again. And what I want to do, as I said, is to pick the line capital L to minimize the sum of the squared lengths of all the green lines. And so let me just write that down. There's the sum over all the lines of the squared green lengths. And if I just write down the algebra, I'm just going to use the Pythagorean theorem. It's not very hard. So I want the length of the green thing. So what I'm going to do, I'm going to take the hypotenuse squared and subtract that line squared. And there it's all written out. I need to know x bar and y bar and a and b, and you can work that out. That's a Pythagorean theorem. I rearrange the algebra a little bit, and so I get all of these coefficients, which are just sums of squares of x minus x bar and y minus y bar. And so these are some scalars I'm going to put into capital X1, capital 2, and capital X3. And then I notice that I can write the sum of squares as this quadratic form. This is a 2 by 2 matrix, and this gives me A1 times capital X1 times A1, so that term gives me there. And so this is what I want to minimize. That is now a 2 by 2 linear algebra problem. And the answer is well known. A and B, those are going to be, that's a unit vector. That's the eigenvector for an eigenvalue of this matrix for the smallest eigenvalue. And the answer is the smallest eigenvalue of a 2 by 2 matrix, which is not hard to do. So the question is, how do I still have to pick x bar and y bar to minimize the smallest eigenvalue. And the answer, not surprisingly, is the center of mass. Right? Just put x bar, y bar, it should be over there somewhere, it's in the center of mass, and that will minimize everything. So it's all very straightforward, and if I were living in 3 dimensions, I'd have a 3 by 3 eigenvalue problem, but it's all the same idea, minimize the smallest eigenvalue. Okay, so that works in a certain number of dimensions. When I'm connected to my nearest neighbors in the plane, but the question is, what can I say about higher dimensions? So what can I prove that sort of generalize, can I come up with an algorithm that provably is as good as the Lipton-Tarjan theorem, that picks square root of n vertices in 2D or something else in higher dimensions? So let's ask ourselves what we should expect in higher dimensions. So the thing is that, what does it mean to generate a graph from being generalize a planar graph? I mean, obviously in 3 dimensions, I can have any graph I want and connect anybody to anybody without edges crossing, right? Because I can always make lines not cross in 3 dimensions. So what I want to do is capture the intuition of being connected to your nearest neighbors in 3 dimensions or 4 dimensions. And so let's ask ourselves what we expect in that case. Suppose I have a 3D mesh of processors. So everybody's connected to your 7 neighbors, north, south, east, and west, and forward and backwards. So they form a cube. And so what do I want to, what's the obvious best way to partition this? Well, you draw a plane down the middle, and it's just going to be the edges crossing that plane. So if this is a little n by little n by little n cubed set of vertices, so I have little n cubed, call it capital N vertices, how many edges have I cut? It's little n squared, or capital N to the 2/3 power. So it's going to be cutting more edges in that case. In the planar case, it was capital N to the 1/2. Now it's capital N to the 2/3. You can see what happens in higher dimensions. But this is what I'd like to attain by an algorithm like the one that I showed you. And so there is an algorithm that works with high probability. So it's a randomized algorithm. And it has a very nice geometric interpretation. So I want to show it to you. So this is how you describe being connected to your nearest neighbors in higher dimensions. And so I'm going to tell you what the theorem says, and then I'll just draw pictures of how the algorithm works. So I'm going to define something called a k-ply neighborhood in d dimensions, and it's a bunch of disks, so look down here to see what the disks are, with the property that no point here in R2 is inside more than k disks. So down here, obviously, these disks just graze one another, they're tangent, so any one point is in at most one disk. So this is a one-ply neighborhood. So now the question is, how do I generate the edges? Well, I'm going to introduce another parameter alpha, and so I'm going to say a graph comes from one of these sets of disks. If you take one of the disks and you grow it a little bit, you grow its radius by a factor alpha, and then it touches some other disks. And whichever one it touches, well, you put an edge there. Okay, it's a perfectly natural notion. So in this case, in this nice simple 2D mesh, this is a 1-1 graph because there's at most one point, every point is inside at most one disk. But if I take a disk and I just grow it by anything bigger than 1, just barely increase its radius, it's going to touch its 4 nearest neighbors, and it gives me that graph. So that's going to be my generalized notion of being connected to your nearest neighbors in any number of dimensions. So the question is, given a graph like that, how do I partition it as well as something that looks as simple as that? And so here's their theorem, and the algorithm is going to be just randomized. We're going to pick a certain kind of random sphere, actually. And the points inside the sphere will be in one partition, the points outside the sphere will be in others. So the question is, how do I pick a random sphere? But here's what the theorem says. Suppose I have a graph of the sort I just showed you. You know, it depends on these two parameters that tell me who's connected to whom. Then it turns out there's a vertex separator that exists, and I will get it by just picking randomly, that has the property that it gives me a partition. If I take out those nodes, then I get the nodes on the left and the nodes on the right. Each one, it's going to be almost load balanced. Each one is going to have a decent fraction of the total number of vertices. So when d equals 2, that says that neither of the two partitions can have more than 3/4 of the total vertices. So it's almost as good as Lipton and Tarjan. Not quite. They said 2/3. This is 3/4, but this works in any number of dimensions. And then the interesting part is how many vertices did I have to take out to do this? And the answer is n to the power, exactly what we were expecting. So in 2D, I'm taking out the square root of n vertices. In 3D, I'm taking out n to the 2/3, and so forth. And so this is exactly the right kind of asymptotic property. And so the question is, how does the algorithm work? The theorem is proved by saying that if you pick a random sphere of a certain kind, then it will work with high probability. And that means it must exist, right? That's all you need as a theorist. But in practice, we will pick a random sphere, and it will work with high probability. So what are we going to do? We're going to choose a sphere in d-dimensional space, which is where the points live. And the edges that cut the surface of the sphere are going to form the edge separator. Then, given an edge separator, we know how to build a vertex separator. We talked about that before. And it turns out choosing S randomly from a certain distribution, I'm about to show you what it looks like, will satisfy the theorem with high probability. So the question is, how do I pick this random sphere? So let me show you just pictures of the geometry of how it works, and I'll do it in 2 dimensions. And so suppose that all my points originally live in a plane. And what I'm going to do, the first step is to do stereographic projection. I'm going to project them onto the surface of this sphere. So that means I'm going to draw, for each point, I'll draw a straight line from the point to the North Pole of this unit sphere. And wherever it intersects, that's the stereographic projection. So now I've put all my points onto the surface of the sphere. So what do I do now? It turns out that there's such a thing, once the points are on a sphere, there's a particular point somewhere inside the sphere called the center point. And it has a property that any plane through the center point divides the points evenly, so that half are on one side and half are on the other. And there's actually a linear programming algorithm in cheaper heuristics to find that center point. Okay? So now what I'm going to do is, how do I get the points onto the sphere so that it's easy to find this center point? What I'm going to do, and I'll draw pictures in a second, I'm going to rotate the points around the origin. So they're all sitting on the sphere. And I'm going to make the and the center point is somewhere in the middle. So I'm going to rotate them, show you a picture in a second. So the center point is right above the origin. It's a distance r above the origin. Then it turns out I want the center point to be at the origin, not just above the origin. And so how do I do that? I'm going to unproject it, unstereographic projection. They're all back in the plane. Just scale them, multiply each point by this magic scalar, project them back on the sphere, and that will put the center point at the origin. And if you think what happens to all the points, I'll show you a picture. They're all spread evenly around the sphere. It kind of randomly distributes all the points around the surface of the sphere. And now all I have to do is pick a random plane through the center point, which is now the origin. And so what do I do when I pick an intersection of a plane and a sphere? I get a great circle. And then I unproject the circle, and that turns into another circle. That's a theorem of geometry. You do stereographic projection, circles turn to circles. And so that random circle is going to be my dividing thing in the original space. So let me now draw a picture to see how it all happens. So here's going to be my graph. And everybody's, and so I put in all the edges, and I want to pick somehow a random now circle and to divide it into the two parts. And as I said, all I care about is the xy coordinates, so I don't need the edges. Let me just throw away all the edges, and that's all the information that I need. And let me now do stereographic projection. And there they all are. They're all sitting on the surface of the sphere by that trick, draw a line through the point in the North Pole. There they are. And there is the center point. By having run the linear programming algorithm, it's that big heavy dot right there. So now what I do is, as I said, I take all this data and I rotate it. You can just imagine rotating the sphere. So the center point is way up at the top, right above the origin. And then I dilate it so the center point moves down to the origin. And when I'm done there, with that step, there it is. There's the center point. And you can see that has spread out all the points relatively evenly across the whole surface of the sphere. And now I just basically take a random plane through the origin. And that intersects the sphere in a great circle, and that's my dividing line. I could have picked any one, randomly, any sphere works with high probability. And so let me project back and look what this means in the original geometry. So there were my original points, and there's the random sphere that I happen to choose. And if I put the edges back in to see what the cut is, that's the cut. So you can see it did, well, maybe a reasonable job of, cutting the edges down the middle, so half are on one side, half are on the other, and I cut as few edges as possible. So that's the algorithm that works with high probability. Any questions about that? I should mention that to prove this was an interesting team of pure mathematicians, including Thurston, who's a famous guy who used to be here on the faculty, and computer scientists. So this is the usual teamwork that it takes. Okay, so let me just summarize, all of this stuff on nodal coordinates. And there are lots of variations in these algorithms. And they're quite efficient. I didn't have to do very much work here. It was sort of just proportional to the number of vertices to a large part. I didn't have to look at the edges. They relied on the intuition that you're only connected to your nearest neighbors in some space, 2D or 3D or whatever. But it doesn't actually depend on where the edges are. And this is pretty common when you have a finite element problem or you're just partitioning real space somehow. But here's an example where I can do arbitrarily poorly by ignoring that information. And so here all of my particles, all my points, vertices, look like they lie on a 2D mesh, but they're just connected in a 1D fashion. And so what would my algorithm just have done? It would have split the thing down the middle there and cut all those edges. Instead, I could just cut one, right? Because this is really a one-dimensional chain. And I would like to be smart enough to do that. But I have to know where the edges are to take advantage of that, right? And so let me just say that there's lots more details, proofs, whatever, at these different websites. So that's the end of the nodal partitioning. And if there are no questions, we can move on to what do you do when you do have edges, and that's what you pay attention to. Okay. So there's a variety of algorithms here. Let me start with the simplest one you could imagine, breadth-first search, right? And just to maybe review a little graph theory. And so given a graph and a root node, pick any old vertex, what does breadth-first search do? It takes all the edges and it classifies them into three different kinds. It creates a tree, a breadth-first search tree. Those are the black edges. And what do those black edges do? They tell you the shortest path from the root to any vertex. And so all of the vertices that are, for example, at this level, level 2 away, they are exactly 2 edges away from the root, which you get by following the tree edges. So it also identifies the horizontal edges. Those are the red ones. Those go from one level to another. From one level to the same level. They stay in the same level. And then there are other edges that are possible, interlevel edges, green ones that go from one level to the next one, but they aren't in the tree. So the claim is that if you have an algorithm and run breadth-first search, that's the only kind of edges you can have. I cannot have an edge from, say, level 1 to level 3. Why is that? What if I had an edge from level 1 to level 3? then that guy over in level 3 is in the wrong level. He's only 2 away from that level. He should have been up there, right? So if this is the definition of breadth first search. Now, this is an algorithm that has been implemented many times. It's in standard packages. Let me just, for the non-computer scientists perhaps who haven't seen this before, just summarize really quickly what the data structure is. It'll be a building block for us. I need something called a queue. So that is a data structure which is also called first in, first out. I put something in. I have 2 operations on it. I can add something to the queue, and I can take, that's NQ, and I can take something out, and it's just in, first out order. And all I'm going to do is process every vertex in this graph in using this queue. So I'm going to put the root in the queue. He's the first one, and I'll mark it. I visited you. And then I'll go to the queue, and while the queue is not empty, I will keep taking vertices out and investigating them. So at the beginning, the only thing in the queue is the root. So I bring them out and I say, who are your neighbors? You have 3 neighbors. I will mark them as all these 3 neighbors are at level 1, and I'll put those neighbors in the queue. And I'll mark them as I visited you before. And then I throw the root away, I'm done. And then I go through the queue and I pull out these guys in order, and I look at all their nearest neighbors who I haven't visited before, and I get everybody at the second level, and so on and so forth. And so that's a nice simple data structure, and there's the code that's also in many libraries. So let's ask ourselves whether this does a decent job of partitioning, or why we should expect it to do that. And just to remind you, here's the picture. And there are 3 different kinds of edges. There's the tree edges, the black ones, the shortest paths from the roots to each vertex. The horizontal ones, which stay at a level. And then the ones that aren't in the tree but go from level I to level I plus 1. And as I said, there are no edges that go beyond 2 levels or more, right? Otherwise, I would have built the wrong tree. So that tells me that if I were to partition by drawing a horizontal line through the middle and saying everybody in, say, levels 0, 1, and 2, you're in one partition, and everybody past you is in a different partition, there's some intuition that says that ought to be a good graph partitioning, because I know that I can't have lots of edges from way up here to way down there. I can see all the edges that connect right in that middle part there. And so if I pick a horizontal line to cut, and I know that it doesn't cut very many edges, that's an easy sort of local thing to try. So let's just do that in the case of a 2-dimensional mesh and ask ourselves whether it does a decent job or not. And so here, here's my graph, and let me start with the root in the middle and run the breadth first search algorithm and see what it decides to do. And what I've done here is I've drawn lines as to where the levels are. So the root is in the middle. He's at level 0. Then its nearest neighbors are in this sort of square annulus. They're at level 1. The next near level 2 is in the next square annulus. Level 3 is in the next square annulus. And so it's just sort of growing outward. And so if I were to use this to partition, then what would it do? It would say everybody in levels 0, 1, and 2 would be in one partition. That's everybody inside the blue square. And everybody outside in the yellow, in levels 3, 4, 5, they'd be in the other partition. And so what would I do? I would basically cut along those lines. So you can imagine growing this. Has this done a good job? I mean, I know what the right answer should be. It should be about the square root of the total number of vertices, right? We know that's the best you can do. Does this work? If I cut there, is that proportional to the square root of the total number of vertices? Yes, right? It's maybe twice as big or something as cutting just exactly down the middle, but it still does a decent job, right? So so this is why intuitively it's not bad, and it's a decent building block to get a starting guess. Okay, so but we can do much better than this, but I just wanted to point this out as a decent starting place. So here's the next one, and that's due to Kernighan finally. And it will take an initial partition, maybe the one that I just suggested from doing breadth first search, and it will iteratively improve on it. And so when they invented this, they came up with an n-cubed algorithm. That's one I'm going to present because it's relatively easy to understand. And later, people got a much faster version of it, ordered number of edges, right? That's as good as you're going to get. You look at each edge once. But it's more complicated, and I'm going to explain the n-cubed algorithm instead. But you would use fiducia Mathei's implementation in practice. So here's the idea of how we're going to iteratively improve a starting guess. So I'm given a graph, and they're edge weights, and I'll assume the node weights are all 1, just keep it easy. And I have an initial guess at a partitioning. The nodes are broken into A union B. And so what I want to do is figure out whether it's worth taking a little bit of A, a little bit of B, and swapping them, right? That's going to be my step. And so what I need to know is to evaluate how good is this partitioning. So cost of A comma B is the cost of the partitioning. It's the sum of all the edge weights that connect A to B, the cross. And so what one step of Kernighan-Lin is going to do, it's going to find some subset of X of A and Y of B with the same cardinality and ask, is it worth swapping them? Is it worth taking X out of A and putting it in B, and Y out of B and putting it in A? And so here's the swap. So I'm going to take A, subtract X, add Y. That's going to be the new A. Take B, subtract Y, add X. That's the new B. And I'll ask, is the new cost, the new T, less than the old cost? And if it is, well, I will think about whether it's worth doing or not. And you'll see that how I do that choice. So to make this, run this efficiently, I need to very quickly be able to compute the new cost for as many possible choices of X and Y very fast, right? So otherwise it'll just be too expensive. I can't afford to reevaluate everything from scratch every time. So here's the clever little bit of algebra that makes it very cheap to say, is it worth swapping these two subsets, X and Y? So I need an efficient formula to update the new cost. And so here's the idea. So for each vertex, I'm going to keep a data structure where I keep track of the sum of all the edge weights from each little a in big A to the other side, to capital B. That's the external cost. But I'm also going to keep the internal cost. That's the sum of all the edge weights from A and little a to everybody else in capital A. Now, why do I keep track of both of those? Well, what would happen if I move little a over to the other side? I would just swap internal and external, right? And so it's going to make it easier to update all the costs, because I just sort of add one and subtract the other. And so, in fact, I'll keep track of that by keeping the difference, the external minus the internal costs. And I'll do analogously, I can imagine computing all these guys for every little b inside of capital B. So the question is, suppose I now want to swap just two vertices, little a in capital A and little b in capital B. Let me swap those. There's the algebra for the swapping. How much does the cost change? And it turns out all I have to do is, three additions and subtractions, and I can get the new cost. Because this guy just negates, so I'm going to just swap dA and dB, just take the negatives, because internal turns into external. Now, the only trouble when I do that, I've counted one edge twice. That's the edge that may connect A to B directly, so I have to subtract that out, because I may have counted it twice. And so this thing in parentheses is the gain. It's how much the new cost decreases from the old cost. Now, the gain may be positive or negative, right? But it may be good or bad. But it's a nice simple formula to compute it. So here are going to be, and so let's suppose I choose to swap it. Then I'm going to do this again and again. I'm going to pick new pairs of little a and little b and ask, do I want to swap them? So I need to update all of these formulas, and we can update them pretty cheaply too. Okay? So finally, given all of this algebra, let me write down the whole algorithm on one slide and tell you what the ideas are. So here's the code and here's the cost. And there's the nasty thing is in red. It's n cubed. I'm going to do this loop n times, and each loop iteration has cost me n squared. So that's where the bad part is. But let me just say what the algorithm does. I'm going to repeat this until I get no more gain, until I can't make any more progress, until swapping doesn't help. And so what I'm going to do is compute all that data structure I was just telling you about, compute all of these d's, and say that unmark all the nodes. So I haven't considered swapping anybody yet. So while there's some unmarked nodes that are possible to consider swapping, find a pair, little a and big A, little b and big B, that has the maximum gain, that decreases the cost the most. So I just look at all of them, and I'm going to mark them, that I'm going to consider swapping you. I'm not going to swap them yet. I'm just going to say I'm tentatively going to swap you, and they're marked. And then I'm going to update all of the costs as though I had swapped them, and keep going. So I'm just going to take all possible pairs. I'll take the first pair, then the second pair, then the third pair. I'm going to just take all the different possible pairs as though I had already swapped the previous ones. Okay? So at this point, I have a sequence of pairs, swapping A1 and A2, swapping, A1 and B1, swapping A2 and B2, and I have gains for them, and they're numbered in the order in which I mark them. So here is the kind of dynamic programming trick that Kernighan-Lin did. They said, well, I now have enough information to decide whether it's worth swapping the first pair, or the first 2 pairs, or the first 3 pairs, or the first 20 pairs. I can do that all at once, and because just by adding the gains. And so I'm going to pick which ones to swap, the first m ones to swap that maximizes the possible gain of the sum of the first m. And why is that a good idea? Because it may be that you get into it may be that it's a good idea to swap a few guys first. Excuse me, let me say it this way. It may be that the gain is negative. It looks bad to swap at the beginning, but that lets you make much more progress later, right? So it gets you out of local optima and gets you to which may not be very good, and gets you to a better one later. And so if the gain is positive of swapping any possible number, then it's worth doing, and you swap them. And then you repeat this loop until you can't make any more progress. And so that's the algorithm. And as I said, the most expensive thing is updating all those costs. That's n cubed, and a later implementation got it down to order the number of edges, so that's optimal. That's good, but it's more complicated. And it gets you out of local minima. So the question is, how often do you have to go through this loop before it converges? And people have been using this for a long time. This is the old data from when they invented this a long time ago. They were running it in very small graphs, and it worked in 2 to 4 sweeps. So it didn't cost that very much. And people have tried to do a bunch of theory on this too. And for random graphs, it looks like the probability of convergence in one step drops exponentially. But in practice, we're going to use this in this recursive way, and it'll be just fine. Okay, so that's Kernahan-Lin. And as I said, it runs in, the new version runs in order the number of edges, but we're going to make it go even faster. Okay, so here's the second building block, which is called spectral bisection. And it was based on some theory about graphs, about spectral properties of graphs from the 1970s, and it was popularized and actually put into code, which has now been, there's a lot of libraries that do this, back in the 90s. And this is Horst Simon, who's the deputy director of LBL now. So that's the same person. So here's the motivation. Suppose I have a vibrating string. You can think of a vibrating string as a one-dimensional graph, right? A bunch of masses connected by springs. So let's say it looks like this. And the question is, let's suppose it vibrates. What's the lowest frequency mode look like? It sort of vibrates like this, right? What's the second highest frequency? The second lowest frequency. It sort of vibrates like this, right? So that tells you how to divide the string into 2, right? One part's up, one part's down. It divides in the middle. And intuitively, that's a good way to divide it in half, right? We're going to do that for arbitrary connected things, so trampoline or whatever you want. But it's going to be the same physical notation. We're going to solve that physics problem. What are the modes of vibration? We're going to solve that exact physics problem. And we're going to take the second lowest frequency and use that to divide the vertices, the ones that go up and the ones that go down. And so I'm going to give you a bunch of and it's going to turn into finding eigenvalues of a matrix that's called the Laplacian. We've heard the Laplacian before, but the Laplacian can be defined for arbitrary graphs. And that's going to be arbitrary connectivity, and that's what we're going to use to do this. And so I will define all those definitions, make all those definitions, and come back and write down the physics problem. And the question is, how do we actually find the second lowest vibrating mode? There's a classical algorithm for that called the Lanczos algorithm. But let me tell you that we now have a sort of a chicken and egg problem. Why am I doing this in the first place? Well, I wanted to optimize sparse matrix vector multiply, right? That was one of my original motivations. And so I want a graph partition. So that means I need to find an eigenvector of a matrix to find the second lowest mode of vibration. That means I'm going to run the Lanczos algorithm. How does the Lanczos algorithm work? It does sparse matrix vector multiply, right? So it sort of sounds like there's no free lunch. But so what's the takeaway here is that if you only want to do 1 or 2 sparse matrix vector multiplies, don't bother. Right? It's not worth all of this cost. But if you're going to do it many times, which is what happens in practice, then this is an overhead. Running Lanczos, doing this partitioning is worth it. And in practice, you often end up doing hundreds or thousands or millions of these sparse matrix vector multiplies, and so it's worth doing this overhead. But there's a cost there. Okay, so let me just go back to the definitions and draw the pictures a little bit better than waving my hands, and then write down the algebra. So here is a vibrating string. There's the lowest frequency. There's the second lowest frequency. And if I actually compute the eigenvectors of this, I get a vector of numbers. And those numbers will have some positive entries and some negative entries. And that's how I'm going to be doing the partitioning. So let me now figure out how I'm going to do that. I have to define two matrices that are associated with a graph. One of them is called the incidence matrix, and the other one is called the Laplacian. And we've seen the Laplacian before for nice regular meshes, but now I have to define it more generally. So what's the incidence matrix of a graph? It's just a different mathematical notation for the graph. So it's going to be a matrix with number of vertices rows, number of edges columns, and I'm just going to put in zeros and ones to record where the edges are. So, so if I look at one particular column, it's associated with an edge. Suppose it's the edge from vertex I to vertex j, then I'm going to put a 1 and a negative 1 in row I and row j, and that indicates that that edge is connected from row I to row j. I'll draw a picture on the next slide. So that's a very simple way to record where all the edges are. And the other graph is a Laplacian. And this is going to be a symmetric matrix. It's going to have one row and column per vertex. And what's on the diagonal? It's going to be the degree. How many edges are connected to each vertex? And the off diagonals are simply going to record where are the edges. So matrix entry ij will be -1 if there's an edge from I to j. And that makes the matrix symmetric because it's, ij, ji are going to be the same, and it's going to be 0 otherwise. So let me just draw some pictures for the simplest graph, which is just one-dimensional, and then also a 2D mesh. And so I've color-coded it here, so the vertices or the nodes are black and the edges are blue. And so here's the incidence matrix, and it has 5 rows for the 5 vertices and 4 blue columns for the 4 blue edges. And so edge 1 connects vertex 1 and 2, and so there's a 1 and a -1, and edge 3 connects vertices 3 and 4, so that's down there and so forth. And there's the Laplacian, and it's almost the same as the Laplacian I showed you earlier when we were solving Poisson's equation, but it's not quite, but you'll see that I don't have to change the physics much to make it the physically right matrix. So there's, go down the diagonal, and it's almost all 2's, except for the guys in the end. They only have one neighbor, and they're -1s in the off diagonal. And here's the two-dimensional case. And let's look at this one first. This looks very much like the 2D Laplacian we had before, except instead of having 4's all the way down the diagonal, since there's only one guy with 4 neighbors, there's only one 4 there. Everybody else has slightly fewer. But if it were big, I'd have lots of 4's down the diagonal. And then -1s for my left, right, and north-south neighbors. And there, similarly, is the incidence matrix. So let me tell you some nice properties of these matrices that are going to let us do the partitioning. So here are the most basic properties of all of these matrices. The first one is that Laplacian is symmetric, right? I defined it that way, right? An off diagonal is ij is -1 if and only if there's an edge from I to j. That makes it symmetric. So what do we know about symmetric matrices? The eigenvalues are real, and the eigenvectors are real and orthogonal. Okay, so that's just a basic thing to know. More interestingly is that if I take the incidence matrix and multiply it by the transpose, I get the Laplacian. And so let's just think about what that means. Let's go back here. I want to take this matrix and multiply it by its transpose. That means I'm going to take the dot product of 2 rows. That's what it means to multiply by the transpose. So I would take the dot product of, let's say, this row with itself. What does that do? It's just going to count the number of 1's in that row. And that's the degree. That's how many edges are attached to it, and that's exactly what goes in the diagonal there. Now what happens if I compute the, take the dot product of the ith row and the jth row to get the ijth entry of the Laplacian? So when is the dot product of the ith row and the jth row going to be non-zero? It's when there's a 1 and a -1 in it. That means whether there's an edge. So I'm going to get a -1 exactly when they're edges. So there is that guy. So what happens when I know that I can write my Laplacian as a matrix times its transpose? What does that tell me about the eigenvalues? This matrix has a square root, so to speak. That means all the eigenvalues are non-negative. So let me just write them down. And so, and they're going to be ordered in that order. Now, I claim the bottom one is 0, for sure. Why is that? So that means I claim that I can just write down, without doing any work, a null vector, at least one null vector of this matrix. So can you see what the null vector is? All 1's. Each row sum is equal to 1. And that's because that's the degree, and I have that's the number of edges, and I get a -1 for each edge, so it better add up to 0. So that's one property, the next property. But even more interestingly, and now we're getting into why the Laplacian tells you lots of interesting things about your matrix. The number of connected components of the graph is equal to the number of zero eigenvalues. Right? So the spectrum of the matrix and the connectivity of the graph are very intimately combined. They're going to be more intimately in a moment. So let's just see why that is. So this is obviously a connected graph. It has one null vector, 1, 1, 1, 1, 1. Suppose I had two copies of this. What would the Laplacian look like? It would be this matrix and then another copy of it it would just be block diagonal. So I'd have one null vector, 1, 1, 1, 0, 0, 0, and then 0, 0, 0, 1, 1, 1. So clearly, for each connected component, I get a new null vector. So the other thing is, so that tells me that the second eigenvalue tells me in some sense, tells me how connected the graph is, right? If lambda 2 is 0, I just said we'll have two connected components at least. If it's positive, I have one connected component. It turns out that if it's tiny, it's not very strongly connected. The size of lambda 2 is going to tell me how easy it is to disconnect the matrix, how easy it is to partition. Okay, and that's going to be the basis of my algorithm. So here again, just to repeat, here's the algorithm. I'm going to compute the eigenvector corresponding to that second largest eigenvalue. And for each, so that's going to give me a vector of numbers. And for each vertex, and there's going to be one number for each vertex in the node in the graph. And I'll just look at the sign. Is it positive or negative? And if it's negative, I'll put it into that partition. And if it's positive or 0, I'll put it in the other partition. So why is this a good idea beyond the intuition of the vibrating string? So here's some theorems, which I won't prove, that explain why it's a good idea. So the first question to ask is that if I do this, then, so all of these guys and all of these guys, at the very least, I would hope that all of the vertices in n minus are connected to one another. That there's a path from every vertex here to somebody else. And similarly for that guy. So it's like partition to the left and the right. I mean, it would be really silly if, for example, I took the even and put that in one partition and the odd and put it into another. That would be a lousy partitioning, because every would be disconnected. In fact, I am guaranteed that the n minuses will all have paths to one another, from one n minus to another, and the n pluses will all have paths to one another, from one to another. So it's sort of, it bisects it in a perfectly reasonable way. And here's the next theorem that says why that second largest eigenvalue tells you how connected you are. Suppose I start with my graph and I remove an edge. What happens to the second largest eigenvalue? It goes down. So it's sort of a monotonic function of how connected the graph is. Every time I pull out an edge, lambda 2 has to either stay the same or decrease. And so it's a nice metric of how connected the graph is. And finally, here's another more tangible way to describe it. So suppose I take my graph, and let's suppose I partition it in any possible way. And the question is, how many edges do I have to cut in order to partition it into n1 and n2? Then it turns out that's proportional to the second largest eigenvalue. Any partition that divides the graph exactly in two has to have 1/4 times the number of vertices times lambda 2 edges in it. So lambda 2 really is a metric of how connected the graph is. And all of these have very elementary proofs that you can read, but and since this theorem was published, there's been an enormous growth of, it's called spectral graph theory. How do you connect properties of the Laplacian to connectivity properties of the graph? But these were the sort of initial classical theorems. Okay, so that's going to be that's sort of the motivation for the algorithm. And so how am I going to do it? I said it's a physics problem. I'm going to take my graph and pretend it's a vibrating, string or trampoline or whatever it is. And so what I need to do is write down a bunch of vertices and with fixed masses, and each edge is going to turn into a spring. I'll write down F equals ma. For this coupled system, I'll get a matrix. And then I'm going to ask, and that's going to describe how the thing vibrates. And then I will ask, does it have fixed modes of vibration? Is there some solution to this F equals ma problem? And those turn out to be the eigenvalues and eigenvectors. So I'm going to show you what this vibrating string looks like, and it's going to turn into the Laplacian. Okay, so let me now just do it for this particular vibrating string. And so I'm going to let x be the, and I'm going to assume it's vibrating up and down. And so, and since those are masses and I'm stretching the spring, I'm going to assume that the stretchiness is, there's a spring constant, and how much it stretches is proportional to the difference between how much that is up and how much that's down. So there I write it down. And so I get spring constant times, -1 times my neighbor to my left, my own value times 2, and minus my neighbor to my right. And when I write down F equals ma, so there's mass times acceleration, mass times x double dot, and there is the expression I just did there, and so the force. And so if I just write that down for all of the vertices here, I get that the mass times the second derivative of all of the positions is the spring constant times, well, that very familiar looking matrix, times that vector. So minus k times now the Laplacian times x, okay? So there's F equals ma. Let me just write it down again and keep going. And so what I want to do is ask, does it have any modes of vibration? So I'm going to ask, is there a solution to this differential equation of the form a constant shape mode times a frequency, that, something that depends just on time. So the alpha is the frequency of vibration. So let me just plug x of t into, F equals ma, and all the sign terms cancel. And I get that x naught, that mode of vibration, is an eigenvector, and alpha squared tells me the frequency. So for this one-dimensional problem, this is incredibly well studied. It's just sine curves. So there's the nice written, explicit expression for all of the frequencies of vibration, and there's the value. Now, the trouble with that example is that it isn't quite the graph Laplacian, right? So remember, the graph Laplacian had 1s in the corner. So this is not exactly the right physics problem. So I have to tell you, how do we modify the physics problem? It's still going to be a physics problem, but it's not this one. So I just need to have a slightly different vibrating string, and this is what it looks like. This gives you exactly the graph Laplacian. So suppose I have a bunch of rods, and on each rod there's a little ring that can move back and forth, right? So, and it's all greased, so there's no friction. And they're all connected by springs. This is my vibrating spring. So if I write down F equals ma for this, I will get the graph Laplacian, right? Because there's only one neighbor here. But let's ask ourselves, what are the natural modes of vibration of this flavor of vibrating spring? Well, if everybody just moves backwards, that's 1, 1, 1, 1. That's the vector. That, and there's no forces created on that. That's a null vector. Or if I move it forward. But what's the other mode of vibration? Just what's your intuition for the second frequency? What's it going to look like? It's going to vibrate like this. Okay, so let me just draw the pictures. So here are the modes of vibration of that one. And so there's the all ones, that's the null vector, right? The springs don't move at all. Here's the second eigenvector, and this is exactly what we want. There's the positive vertices. They all go into the one partition. There's the negative ones. They all go into the other partition. And, and there are more eigenvectors too. So now let me just show you what it looks like for a slightly more interesting graph. And call it a broken trampoline. So this is a planar graph. And so here is what the graph looks like, and the original mesh. And so what I'm going to do is show you from different points of view what the second eigenvector looks like. So what do you think this thing is going to do when it vibrates? Let me use my hand. So here's the broken trampoline. It's going to vibrate like this. Okay? And that's what we see here. And so what I've done is I've circled all the vertices where it goes down and left uncircled all the vertices where it goes up. And here is a top view. It's a little hard to tell. And here's the view front on, where you can sort of see my fingers waving up and down. So part goes up, part goes down, and it's pretty natural. That's a good place to partition it, right along those few edges there. And that sort of breaks the graph in half. Now, and that's what you get from that particular physics problem. So some people say, well, why don't I just, this is good for graph partitioning, for bisection, right? But what if I have 4 processors or more? What I said earlier is that I could just do this recursively, but I could also use a higher eigenvector. Some people try that, so let me just look at that picture and see what happens. So what I'm doing here is saying, what does the 4th eigenvector look like, right? So now this is the 4th mode of vibration. And so, I've circled the negative, circled in this case, the positive components, and left uncircled the negative ones. So that tip is going up. So you can see that tip is going up. It's going up in the back, and that's going down, and that's going down. So here I could cut along that edge, and that edge, and I could break it up into 4 all at once. And so some people do that. But bisection might be a little bit more stable. Okay, So now I get to the point, as I said, where I need to compute. I have the graph Laplacian. I need to get its second largest eigenvalue and its corresponding eigenvector, lambda 2 and v2. And so what is the algorithm? So here it is, and I'm not going to talk about it in too much detail. I just want to show you what work it does. And what it does is it starts with any old initial guess that you like, an arbitrary starting vector. What it's going to build iteratively is a small matrix which approximates the large matrix. So my original matrix, what's the dimension? It's the number of vertices. I want to build something much, much smaller whose eigenvalues and eigenvectors are close to the original one. So how is that going to work? I'm going to take that original vector, and I'm going to do these operations. I'll scale it. That's a BLAS1 operation. The bottleneck is doing a matrix vector multiply. So I'll take that vector and multiply it by A. That's the expensive step. And then I do a bunch more BLAS1 operations, Saxby's and dot products and so forth. And out of this are going to come a bunch of constants, A1, B1, A2, B2. I'm going to fill up this tridiagonal matrix. Suppose I take k steps of this algorithm, do k sparse matrix vector multiplies. I'll take those k constants and fill them up into this little tridiagonal matrix. It turns out the eigenvalues of this little matrix are good approximations for the original eigenvalues of the big matrix. And so the second smallest eigenvalue of t will be a good approximation for the second smallest eigenvalue of the original graph Laplacian. And I can also get the eigenvectors out of it. And so here is the no free lunch, or the chicken and egg problem. I have to do sparse matrix vector multiply in order to optimize sparse matrix vector multiply. But hopefully I won't have to do this very often. Okay, so just to summarize here, the Laplacian is going to represent the graph connectivity. It has everything encoded in it that it's identical to the graph. The second eigenvector, for all these physics intuition reasons and some theorems of Fiedler and others, gives a graph bisection, which I know is close to doing as well as possible. And it's going to be implemented by the Lanczos algorithm, which is doing sparse matrix vector multiply. But hopefully we won't have to do it very often in order to partition my big matrix, which I will then do sparse matrix vector multiplies many times. So that is a possible stopping point, but I guess we still have a while. So did you want to make an announcement?
It's very short.
Well, go ahead. This is a good time before I go on to the next part.
Well, so it was just a reminder that homework, the part 1 of homework 2 is due tomorrow. So go ahead and remember that there is a write-up also. Don't just worry about the code up until the last minute. You also have to tell us kind of like what you tried implementing and what worked and what didn't. And the second part of the assignment, which is going to be about coding GPUs, will also be up at some point later today.
Okay. So let me, I won't be able to finish. All right, so this is how far we've gotten in the lecture. And I will not be able to finish multi-level acceleration, but let me at least begin it and find a good stopping point. So I want to partition the graph, and I've given you a lot of algorithms for doing that, but it's too big, right? It's not, if I were to try to run spectral bisection, I would have to do so many sparse matrix vector multiplies on the original large graph, it wouldn't be worth it. Or if I'm doing Kernighan-Lin, even though it's proportional to the number of edges, it's just too expensive. So here's the idea. I'm going to take my original graph and approximate it somehow by a coarse approximation. So the subscript c means a coarse approximation. So n sub c is half as many vertices. E sub c is half as many edges or smaller. And I'm going to partition that smaller problem instead. And I'm going to use that to get a starting guess for my original partitioning. And all of the algorithms I've told you can benefit by having good starting guesses. And then I'm going to iteratively improve it. And so I'm going to apply that same idea recursively. So let me just show you here what the overall scheme of the algorithm is. And this is going to be the high-level code into which we can plug Kernighan-Lin or Spectral or anything, depending on how we choose to do these steps. So I'm going to define this recursively. It's going to take nodes and edges as an input, and it's going to output a partition. And if you give me a small enough graph, I will just do it directly. That's sort of the base case. So once I get fewer than, I don't know, a few hundred or a few thousand vertices, just run one of the algorithms I already showed you and return that. Otherwise, what I'm going to do is do that coarsening, and depending on whether it's Kernighan-Lin or spectral, there are different ways to coarsen it to take every other vertex or every other edge, and I'll probably go into that next time. Then I call this subroutine recursively to get a coarse partitioning, so n sub c plus and n sub c minus are the partitioning of the coarse vertices. Then I need to expand, so that's and how I expand this subset of vertices to a partition of the original set of vertices is going to depend on how I did the coarsening. So these two go together. And then I'm going to iteratively improve things. And as I said, Kernighan-Lin does iterative improvement in its, in its nature, and Lanczos does as well. And that's what I'm going to improve. And so next time, what I'm going to do is explain how this works, how I take the coarse graph, take one of half the size, take one of half the size, finally partition it at the bottom. So there's my partition that I finally return from the base case. Then I return up here, and that original partition turns into this black one. Then I refine it and get the green one. The green one's better. Then I pass that up. That turns into the black partitioning, my initial guess for that one. I refine it, get the green one. And I pass that back up, take the black one and refine it to get the green one, which is my final answer. So that's going to be the picture that I will do in more detail next time. Okay. And are there any questions about any materials? I think this is the best stopping place. So went a little faster than I thought.